Subscribe to the channel so you don't miss out on any of these videos. Imagine the vastness of space, an endless ocean of mystery and motion, where forces we barely understand shape everything we know. Among these mysteries lies something fascinating, almost alien: magnetic bubbles called plasmids. They're invisible to the naked eye, but they hold secrets about the forces driving the universe. What if I told you that these plasma-filled bubbles might be key to understanding solar flares, how planets protect themselves from cosmic radiation, and even the strange behavior of interstellar matter? Stick around, because once you learn about plasmids, you'll never look at the cosmos the same way. To truly grasp what plasmids are and why they matter, you first need to understand the medium they exist in: plasma. Plasma isn't like the solid ground you stand on, the liquid water you drink, or the gas you breathe. It's the fourth state of matter, made up of charged particles like ions and electrons, and it behaves in ways that often defy common sense. Plasma makes up 99% of the visible universe. Stars, including our Sun, are massive plasma spheres. The auroras dancing at Earth's poles? Plasma. Even lightning on a stormy night is a form of plasma. Plasmids are a step beyond, forming when magnetic fields trap and contain plasma into distinct bubble-like structures. But they're not just floating aimlessly in space. They're dynamic, unpredictable, and sometimes downright explosive. One of the most intriguing places where plasmids appear is in solar flares. Picture the Sun, a constant nuclear inferno, hurling massive amounts of energy into space. Solar flares are sudden eruptions on the Sun's surface, releasing immense energy in the form of light, heat, and charged particles. But here's the kicker: plasmids often form in the aftermath of these events. As the Sun's magnetic field twists and snaps like an overstretched rubber band, plasmids are created in a process known as magnetic reconnection. These bubbles, filled with plasma and magnetic energy, shoot out into space like cosmic fireworks. Scientists believe that studying these plasmids can help us predict solar storms, which can disrupt satellites, power grids, and even the technology we depend on every day. But plasmids aren't just limited to the Sun. They play a crucial role in planetary magnetospheres, the invisible shields protecting planets like Earth from solar winds and cosmic radiation. The Earth's magnetosphere is like a magnetic cocoon, stretching out into space and deflecting harmful particles. Yet, within this protective bubble, plasmids are constantly forming and moving. Imagine Earth's magnetic field being pulled by solar winds, stretched like taffy, and then snapping back. This snapping action creates plasmids, which are then flung into the far reaches of Earth's magnetic tail. These plasmids carry energy and particles away from Earth, helping to balance the constant tug-of-war between our planet and the Sun. Now let's zoom out even further, beyond our solar system, into interstellar space. Here, plasmids take on an even more mysterious role. Between stars, there's a vast, sparse medium called the interstellar medium, made of gas, dust, and plasma. Magnetic fields crisscross this space, and plasmids are thought to form in the turbulent interactions between these fields. Some scientists speculate that plasmids might even help transport energy and particles across unimaginable distances, acting like cosmic messengers. Others believe that plasmids could explain strange phenomena, like bursts of radio waves from deep space or the formation of cosmic jets shooting out from black holes. But what makes plasmids so intriguing isn't just where they show up, it's how they behave. These magnetic bubbles aren't static. They're constantly in motion, evolving, and interacting with their surroundings. They can merge, split apart, or collapse in spectacular bursts of energy. In many ways, they're like living entities, adapting to the environment they're in. This dynamic nature makes them challenging to study, but it also means they could hold answers to some of the biggest questions in astrophysics. For example, understanding plasmids could unlock the secrets of magnetic reconnection, the process that drives everything from solar flares to auroras. Magnetic reconnection happens when magnetic field lines break and reconnect, releasing massive amounts of energy. Plasmids are often the byproducts of this process, but they could also be the key to understanding how it works. By studying plasmids, scientists hope to develop better models of magnetic reconnection, which could improve everything from space weather predictions to nuclear fusion research here on Earth. And then there's the potential connection between plasmids and cosmic structures like black holes and pulsars. Some researchers think that plasmids could help explain how black holes generate powerful jets of particles that shoot across galaxies. These jets, often seen in distant quasars, are among the most energetic phenomena in the universe. Could plasmids be the missing piece of the puzzle? It's a tantalizing possibility. But perhaps the most mind-bending idea is that plasmids could play a role in the search for extraterrestrial life. If plasmids can form naturally in different environments, could they create conditions suitable for life, or even act as carriers of biological material? It's a wild thought, but in a universe as vast and strange as ours, it's worth exploring. Plasmids are more than just a scientific curiosity. They're a reminder of how much we still have to learn about the universe. They're tiny compared to galaxies but monumental in their impact, influencing everything from solar storms to interstellar travel. Studying them isn't just about understanding space. It's about understanding the forces that shape our world and the cosmos beyond. The story of plasmids is still being written. With every new observation, every experiment, and every theory, we get a little closer to unraveling their mysteries. But for now, they remain enigmatic, floating in the vast expanse of space, waiting for us to discover their secrets. And as we continue to explore, one thing is clear: plasmids are proof that the universe still has plenty of surprises in store. If plasmids feel like an abstract concept, let's dig deeper into their core nature. These magnetic bubbles might seem intangible, but they follow well-defined physical laws that scientists are working tirelessly to understand. At their heart, plasmids are governed by the interaction between plasma and magnetic fields, and it's this interaction that makes them so fascinating. Plasma itself is already a wild and chaotic substance. Imagine a sea of charged particles, constantly colliding and generating electric currents. When magnetic fields trap plasma in a localized area, a plasmid forms, and the results can be spectacular. One of the most well-documented environments for plasmid activity is the Magnetosphere, the protective magnetic shield surrounding planets like Earth, Jupiter, and Saturn. In Earth's case, the Sun constantly bombards our magnetosphere with solar wind, high-speed streams of plasma traveling millions of miles per hour. This constant pressure stretches Earth's magnetic field into a long tail that trails away from the Sun, known as the magnetotail. It's within this tail that plasmids frequently emerge. Here's how it happens. As solar wind pushes against Earth's magnetic field, magnetic reconnection occurs in the stretched magnetotail. This process creates plasmids, which are then ejected into space, carrying energy and particles with them. Scientists have observed these plasmid ejections during geomagnetic storms, which can cause stunning auroras but also disrupt satellites, communication systems, and even power grids. Understanding these ejections is crucial for predicting space weather, which has become increasingly important as we rely more on technology vulnerable to solar activity. Jupiter, with its massive magnetic field, offers another fascinating example of plasmid activity. Unlike Earth, Jupiter's magnetosphere is dominated by its volcanic moon, Io, which spews out enormous amounts of sulfur dioxide gas. This gas is ionized and forms a plasma torus around the planet, feeding Jupiter's magnetosphere with energy. Plasmids are regularly created as this plasma interacts with Jupiter's magnetic field, contributing to the planet's intense auroras, some of the most powerful in the solar system. By studying these plasmids, scientists hope to uncover more about the relationship between magnetic fields and plasma, not just at Jupiter but across the cosmos. The story gets even more intriguing when we leave the confines of our solar system and venture into interstellar space. The interstellar medium is a turbulent environment where magnetic fields and plasma are constantly interacting. Plasmids here aren't constrained by planetary or solar systems. They exist on a much larger scale, influenced by the galactic magnetic field. Some researchers believe that plasmids could help explain how energy and matter are transported across the galaxy. For example, when supernovae explode, they release enormous amounts of plasma and magnetic energy into the surrounding space. This chaotic aftermath could give rise to plasmids, which might then carry particles and energy to distant regions, influencing star formation and the distribution of cosmic dust. Plasmids might also be a key to understanding one of the greatest mysteries in astrophysics: fast radio bursts, FRBs. These are incredibly brief but intense bursts of radio waves that seem to originate from far outside our galaxy. While their exact cause is still unknown, some theories suggest that plasmids created during magnetic reconnection events near neutron stars or black holes could be responsible. If true, this would link plasmids to some of the most extreme environments in the universe, further highlighting their importance. But the mysteries of plasmids don't stop there. Some scientists have proposed that plasmids could play a role in the formation of cosmic jets, beams of particles and energy that shoot out from black holes, neutron stars, and other energetic cosmic objects. These jets are among the most powerful phenomena in the universe, capable of traveling across entire galaxies. While the mechanisms behind these jets are still debated, plasmids might provide the missing piece of the puzzle. Magnetic reconnection in the accretion disks around black holes could generate plasmids, which then merge and accelerate, forming the backbone of these awe-inspiring jets. On a more speculative note, there's even the idea that plasmids could be connected to the mysterious dark matter that makes up a significant portion of the universe's mass. While this is far from proven, it's an exciting avenue of research. If plasmids can form in various environments, could they also exist in forms we haven't yet detected, potentially bridging the gap between ordinary matter and the elusive dark matter? The technological implications of studying plasmids are just as exciting as the astrophysical ones. By observing how plasmids form, move, and interact, scientists can apply these principles to create better models for nuclear fusion, a potential source of nearly limitless, clean energy. Fusion reactors, like tokamaks, rely on plasma confined by magnetic fields, a setup strikingly similar to natural plasmids. By mimicking the stability and energy dynamics of plasmids, researchers hope to unlock more efficient ways to sustain fusion reactions, bringing us closer to a sustainable energy future. Plasmids are also a focus for space exploration technologies. Understanding how they form and behave could help engineers design spacecraft that can better navigate through plasma-filled regions, such as the solar wind or the magnetospheres of other planets. As we prepare for missions to Mars, Europa, and beyond, this knowledge will be critical for ensuring the safety and success of these journeys. The story of plasmids is a testament to the interconnectedness of the universe. From the tiniest particles of plasma to the colossal structures of interstellar space, plasmids serve as a bridge between scales, linking phenomena that might otherwise seem unrelated. They're a reminder that even in the vast emptiness of space, there's a constant interplay of forces, shaping the cosmos in ways we're only beginning to understand. And perhaps the most exciting part is that we're just scratching the surface. As telescopes become more powerful, as spacecraft venture further, and as our computational models grow more sophisticated, plasmids will undoubtedly reveal even more about the universe's hidden mechanisms. For now, they remain one of space's most captivating mysteries, a small but significant piece of the cosmic puzzle. The study of plasmids continues to redefine our understanding of how energy and matter flow throughout the cosmos. Their significance extends beyond their immediate environments, offering clues about broader cosmic processes and phenomena. To appreciate the depth of this research, it's essential to explore how modern science investigates plasmids, and what this means for the future of astrophysics, planetary science, and even human technology. One of the critical tools for studying plasmids is direct observation through space missions. Spacecraft such as NASA's Themis, Time History of Events and Macro-Scale Interactions During Substorms, and ESA's Cluster mission have been pivotal in uncovering how plasmids behave in Earth's magnetotail. Themis, for example, has recorded data showing how plasmids are formed during geomagnetic substorms, sudden bursts of energy that travel through Earth's magnetosphere. By analyzing these substorms, scientists can map the intricate dance between magnetic fields and plasma, helping to predict space weather events that might otherwise catch us off guard. Another remarkable achievement in plasmid research comes from spacecraft exploring other planets. Missions like Juno, currently studying Jupiter, have observed how plasmids contribute to the planet's dynamic auroras. Juno's instruments can detect the energy and particle flows associated with these plasmids, revealing insights into Jupiter's powerful magnetosphere. Similarly, missions to Saturn, like Cassini, have explored the unique interactions between plasmids and Saturn's rings, offering a glimpse into how these magnetic bubbles influence the structures around them. But space missions are only part of the equation. Ground-based observatories, especially radio telescopes, play a crucial role in detecting plasmid-related phenomena. Fast radio bursts, FRBs, for instance, are often observed by powerful arrays such as the Canadian Hydrogen Intensity Mapping Experiment, CHIME, or the Parkes Observatory in Australia. While FRBs are still shrouded in mystery, the possibility that plasmids could be involved has spurred astronomers to focus their attention on regions where magnetic reconnection might occur, such as near neutron stars or black holes. Plasmid research is also deeply rooted in theoretical and computational modeling. The behavior of plasma in a magnetic field is notoriously difficult to predict, as it involves highly complex, nonlinear processes. To tackle this, scientists use supercomputers to simulate magnetic reconnection and plasmid formation. These simulations provide a controlled environment to test hypotheses and refine our understanding of how plasmids behave in both natural and experimental conditions. One exciting area of simulation research involves scaling up our understanding of plasmids to cosmic proportions. In interstellar space, where the galactic magnetic field governs the movement of plasma, plasmids could act as agents of energy transfer across vast distances. By modeling these interactions, researchers hope to understand how energy is distributed throughout galaxies, influencing star formation and the overall structure of the universe. This line of inquiry has profound implications, suggesting that plasmids might be one of the mechanisms connecting small-scale plasma physics with large-scale cosmic evolution. There's also a growing interest in the role plasmids might play in one of the most puzzling aspects of the universe: the origin of cosmic magnetic fields. Scientists have long debated how these fields are generated and maintained, a question tied to the so-called magnetic dynamo effect. Plasmids, with their ability to transport magnetic energy, could be an essential part of this process. If confirmed, this would place plasmids at the center of not just localized magnetic interactions but the very structure of the universe itself. As we dig deeper into the cosmic significance of plasmids, it's impossible to ignore their implications for advanced technology. Plasma physics, inspired by natural plasmids, is already shaping the future of energy production. Nuclear fusion reactors like ITER, the International Thermonuclear Experimental Reactor, aim to replicate the conditions of the Sun, using plasma confined by magnetic fields to generate enormous amounts of energy. Plasmids, which naturally achieve such confinement, are a model for optimizing these reactors. By studying how plasmids form and maintain their structure, engineers hope to design more efficient magnetic confinement systems, bringing us closer to a sustainable energy revolution. The potential applications of plasmoid research extend even further. For instance, spacecraft propulsion systems might one day leverage the principles of plasmids to navigate through plasma-rich environments like the solar wind or Jupiter's magnetosphere. By harnessing the natural interactions between plasma and magnetic fields, future spacecraft could achieve higher speeds and greater efficiency, enabling missions to distant planets and even interstellar space. Plasmids also offer tantalizing possibilities for communication technologies. If plasmids can generate or influence radio waves, an idea supported by their potential connection to fast radio bursts, then they could be used to develop new ways of transmitting information across vast distances. This could revolutionize how we communicate in space, enabling faster and more reliable transmissions for deep space missions. On a philosophical level, the study of plasmids challenges us to rethink the nature of the universe. These seemingly simple magnetic bubbles are a reminder that even in the emptiest regions of space, there is a constant interplay of forces and energies shaping the cosmos. Plasmids bridge the gap between the microscopic and the macroscopic, showing how small-scale processes can have far-reaching consequences. They're a testament to the interconnectedness of all things, from the swirling plasma in a laboratory experiment to the sprawling structure of a galaxy. As our understanding of plasmids grows, so too does our appreciation for the complexity and beauty of the universe. These magnetic bubbles, often invisible to the naked eye, hold the key to unlocking some of the most profound mysteries of space. They remind us that even in the vastness of the cosmos, there are intricate patterns and relationships waiting to be discovered. The journey to fully understand plasmids is far from over. Every new observation, every refined simulation, brings us closer to uncovering their secrets. And as we continue to explore this fascinating phenomenon, one thing is clear: plasmids are not just a curiosity of plasma physics. They are a window into the fundamental forces that shape our universe, a bridge between the known and the unknown. Plasmids represent a microcosm of the universe's immense complexity, embodying the intricate dance between energy, matter, and magnetism. While they are inherently elusive, their influence is both observable and profound, impacting everything from small-scale plasma interactions to the formation of large-scale cosmic structures. To truly understand the full scope of plasmid significance, we must venture further into the detailed mechanisms of their behavior, their relationship with the universe, and their potential as tools for advancing human understanding and exploration. One of the most intriguing aspects of plasmids is their potential role in the transport of energy. In many ways, plasmids act like cosmic messengers, ferrying magnetic energy across vast distances in space. When plasmids form, they carry with them a snapshot of the conditions under which they were created, specific magnetic field configurations, plasma densities, and temperatures. As they move through space, these plasmids can transfer energy and momentum to other plasma regions, creating ripple effects that may influence phenomena on planetary, stellar, and even galactic scales. Take, for example, the relationship between plasmids and magnetic reconnection. Magnetic reconnection is a fundamental process that occurs in plasmas when magnetic field lines break and reconnect, releasing immense amounts of energy. This process is not only responsible for creating plasmids but also for driving events such as solar flares, coronal mass ejections, and auroras. In these scenarios, plasmids are the intermediaries through which the energy unleashed by reconnection is distributed. Without plasmids, the energy released in these dramatic cosmic events might dissipate in less organized or impactful ways. In interstellar space, plasmids may play a role in shaping the structure of the interstellar medium, ISM, the vast expanse of gas and plasma that lies between stars. The ISM is far from uniform. It contains regions of varying density, temperature, and magnetic strength. Plasmids, moving through this medium, could act as agents of change, mixing and redistributing material while influencing the magnetic landscape. This mixing could, in turn, affect star formation by altering the density of gas clouds, one of the key ingredients in the birth of stars. Zooming out even further, plasmids might have implications for the evolution of galaxies. Galactic-scale magnetic fields, though still not fully understood, are known to play a crucial role in the behavior of galaxies. These magnetic fields influence the motion of gas and stars, the formation of spiral arms, and even the behavior of supermassive black holes at galactic centers. Plasmids, as carriers of magnetic energy, could be part of the mechanism that sustains and redistributes these galactic magnetic fields over time. If this is true, then plasmids are not just localized phenomena but essential components of the cosmic ecosystem. The connection between plasmids and black holes offers another fascinating avenue of exploration. Black holes, especially the supermassive ones at the centers of galaxies, are surrounded by accretion disks of gas and plasma. These disks are highly dynamic environments where magnetic fields play a significant role. Magnetic reconnection and plasmoid formation could occur in these environments, contributing to the production of powerful jets of particles that shoot out from the poles of black holes. These jets, which can extend for thousands of light years, are among the most energetic phenomena in the universe. If plasmids are indeed involved, they might hold the key to understanding how these jets form and sustain themselves. Closer to home, plasmids offer invaluable insights into the behavior of Earth's magnetosphere. The magnetosphere is a protective bubble of magnetic field that shields our planet from the solar wind, a continuous stream of charged particles emitted by the sun. However, this shield is not impervious. During geomagnetic storms, When the solar wind intensifies, plasmids can form in the magnetotail and release energy back toward Earth. This process, known as the substorm current wedge, is responsible for spectacular auroras but also for potential disruptions to satellites, power grids, and communication systems. Understanding plasmids in this context is critical for predicting and mitigating the effects of space weather. The study of plasmids also extends into experimental and laboratory settings. By recreating the conditions under which plasmids form, scientists can study their properties in controlled environments. Devices like tokamaks and stellarators, which are designed to confine plasma for nuclear fusion, often produce plasmid-like structures. These experimental plasmids are not just curiosities, they are essential to the quest for achieving sustainable fusion energy. By studying how plasmids form and behave, researchers hope to improve the efficiency and stability of fusion reactors, bringing us closer to a future powered by the same processes that fuel stars. Beyond energy production, plasmids hold promise for advancing space travel. The idea of using plasma-based propulsion systems, inspired by natural plasmids, has gained traction in recent years. These systems could use magnetic fields to generate and direct plasma, creating thrust with high efficiency and low fuel requirements. Such technology could revolutionize space exploration, enabling missions to distant planets, moons, and even interstellar space. Plasmids might also play a role in the search for extraterrestrial life. Magnetic reconnection and plasmid formation are universal processes, occurring wherever plasma and magnetic fields interact. If plasmids are influencing the chemistry of planetary atmospheres or interstellar clouds, they could be indirectly shaping the conditions for life to emerge. For example, the energetic particles and radiation associated with plasmids might trigger chemical reactions that produce complex organic molecules, the building blocks of life. As we continue to explore these possibilities, the study of plasmids is poised to unlock new frontiers in science and technology. Each discovery adds another piece to the puzzle, revealing not just the mechanisms behind plasmids but also their broader significance in the universe. The more we learn, the more we realize how interconnected everything is, from the smallest plasma particle to the largest cosmic structures. The beauty of plasmids lies in their dual nature. They are both universal and unique, both simple and complex. They remind us that even in the emptiness of space, there are dynamic forces at work, shaping the cosmos in ways we are only beginning to understand. As research continues, plasmids will undoubtedly play a central role in unraveling the mysteries of space, offering insights that could transform our understanding of the universe and our place within it. Plasmids also open the door to questions about the fundamental nature of plasma itself. Plasma is often referred to as the fourth state of matter, but its behavior is distinct from that of solids, liquids, or gases. Plasma is highly influenced by electromagnetic forces, and plasmids epitomize this influence. In understanding plasmids, scientists delve deeper into the dynamics of magnetic field lines, their interactions, and the conditions under which they bend, break, and reconnect. This investigation sheds light on phenomena that are not only cosmic but also applicable to industrial and technological advancements on Earth. One particularly compelling area of research focuses on the stability of plasmids. In space, plasmids are often transient. They form, evolve, and dissipate over relatively short periods. However, in laboratory settings, scientists are investigating ways to create stable plasmids that can maintain their structure for longer durations. These efforts have significant implications for nuclear fusion, where the ability to confine plasma effectively is crucial. If stable plasmids can be engineered, they might serve as a stepping stone toward achieving controlled, sustained fusion reactions. The stability of plasmids is governed by a delicate balance of forces. On one hand, the internal pressure of the plasma works to expand the plasmid, while on the other, the surrounding magnetic field acts as a confining force. This interplay creates a dynamic equilibrium that defines the plasmid's shape and lifespan. Small disturbances can tip this balance, causing the plasmid to fragment or dissipate. By studying these instabilities, scientists hope to uncover strategies for maintaining control over plasmid behavior, whether in experimental reactors or space applications. Another exciting development in plasmid research is the use of advanced computational models and simulations. The behavior of plasmids is governed by complex equations that describe the interactions of magnetic fields, electric currents, and plasma particles. These equations, while daunting in their complexity, can now be solved with the help of high-performance computing. Simulations allow researchers to recreate plasmid dynamics in virtual environments, exploring scenarios that might be impractical or impossible to observe directly. These models provide valuable insights into the conditions under which plasmids form, their energy transport mechanisms, and their interactions with other cosmic phenomena. As the computational power available to scientists continues to grow, so too does the fidelity of these simulations. Modern models can capture intricate details of plasmoid formation and evolution, revealing behaviors that were previously hidden. For instance, simulations have shown how plasmids can merge to form larger structures or fragment into smaller ones, depending on the surrounding magnetic environment. These findings not only enhance our theoretical understanding of plasmids but also guide observational efforts, helping astronomers identify and study plasmid-related phenomena in space. Observations, of course, remain a cornerstone of plasmid research. The advent of advanced telescopes and space probes has revolutionized our ability to study plasmids in situ. Instruments like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter have provided unprecedented views of the Sun's corona, where plasmids form during solar flares. These missions have captured high-resolution data on the temperatures, densities, and magnetic fields associated with plasmids, offering a detailed picture of their role in solar activity. Similarly, spacecraft exploring planetary magnetospheres, such as NASA's Themis mission and the European Space Agency's Cluster mission, have provided direct measurements of plasmids in Earth's magnetotail. These observations confirm theoretical predictions while also uncovering unexpected behaviors, such as the formation of plasmid chains, sequences of plasmids that form and propagate in quick succession. Such findings challenge existing models and inspire new avenues of inquiry. Plasmid chains, in particular, are a fascinating phenomenon. These structures suggest that plasmid formation is not an isolated event but part of a larger, interconnected process. The idea of plasmid chains raises questions about the conditions that give rise to them and their implications for energy transfer in space. Are these chains a common feature of magnetized plasma environments, or are they unique to certain conditions? Do they represent a more efficient mode of energy transport compared to individual plasmids? These are just a few of the questions driving current research. The role of plasmids in astrophysical jets is another area of intense interest. Jets are highly collimated streams of plasma that emerge from a variety of cosmic sources, including young stars, neutron stars, and black holes. Observations suggest that these jets are often punctuated by knots or blobs of plasma that could be interpreted as plasmids. If so, plasmids might be a key component in the mechanics of jet formation and propagation. Astrophysical jets are among the most energetic phenomena in the universe, and their origins remain a topic of debate. One hypothesis is that magnetic reconnection in the accretion disk surrounding these objects produces plasmids, which are then ejected along the jet axis. As these plasmids travel outward, they interact with the surrounding medium, generating shocks and emitting radiation across the electromagnetic spectrum. This model not only explains the observed structure of jets, but also highlights the potential universality of plasmid-related processes. Even on smaller scales, plasmids offer insights into the behavior of plasma in diverse environments. In Earth's upper atmosphere, for example, plasmids contribute to the dynamics of the ionosphere and the formation of auroras. By studying these localized plasmids, scientists can develop better models of space weather and its impact on technology. Similarly, plasmids in laboratory plasmas provide a testing ground for theories that can be applied to both terrestrial and cosmic contexts. As our understanding of plasmids deepens, their potential applications continue to expand. In addition to their relevance for fusion energy and space propulsion, plasmids could play a role in advanced materials research. The intense magnetic fields and temperatures associated with plasmids create unique conditions for studying the properties of matter. By leveraging these conditions, scientists might discover new states of matter or develop novel materials with unprecedented properties. The implications of plasmid research extend even further into the realm of fundamental physics. Plasmids offer a natural laboratory for studying the interplay between electromagnetic forces and relativistic effects, shedding light on the behavior of charged particles at high energies. This research could provide clues about the fundamental forces that govern the universe, from the microcosm of quantum mechanics to the macrocosm of cosmology. Ultimately, the study of plasmids is a testament to the power of curiosity and the interconnectedness of science. These enigmatic structures, born of magnetic fields and plasma, bridge the gap between theory and observation, between the laboratory and the cosmos. They remind us that even in the vast emptiness of space, there are dynamic forces at work, shaping the universe in ways we are only beginning to understand. The exploration of plasmids has also unlocked new perspectives on how energy is stored and released in the cosmos. Energy released through magnetic reconnection, which plays a pivotal role in plasmid formation, represents one of the most efficient ways to convert magnetic energy into kinetic energy and heat. This conversion process powers phenomena like solar flares, geomagnetic storms, and even cosmic jets. By studying plasmids, researchers are uncovering the universal principles governing energy conversion in plasmas, providing insights applicable to many fields of science and technology. Plasmids also offer intriguing clues about turbulence in plasma systems. Turbulence, the chaotic and unpredictable behavior of fluid or plasma flow, is one of the most complex and least understood phenomena in physics. In magnetized plasma, turbulence is closely linked to magnetic reconnection and plasmid formation. Observing how plasmids interact within turbulent environments helps scientists decipher the complex dynamics at play. Turbulent plasmas are common in many astrophysical settings, from the sun's corona to interstellar clouds, and understanding them is crucial for advancing our knowledge of these environments. One surprising discovery in plasmid research is the self-organization of these magnetic structures. Despite their chaotic origins in turbulent reconnection events, plasmids often exhibit regular patterns and behaviors. This self-organization challenges traditional assumptions about disorder in plasma systems and suggests that even in the most chaotic conditions, underlying principles of order and structure persist. Scientists theorize that this self-organization could reveal new laws of nature, guiding the behavior of systems far beyond the scope of plasmid research. Another fascinating aspect of plasmids is their role in the transport of particles and energy across vast distances. For instance, in Earth's magnetosphere, plasmids act as energy packets, carrying charged particles and electromagnetic energy from one region to another. These particles can travel from the distant magnetotail back toward Earth, where they interact with the atmosphere to produce auroras. The efficiency of this transport mechanism has implications not only for space weather prediction but also for understanding particle acceleration in other cosmic settings, such as supernova remnants and black hole jets. The particle acceleration associated with plasmids is particularly intriguing. When plasmids form and evolve, they create regions of intense electric fields that can accelerate charged particles to high energies. These accelerated particles emit radiation that can be observed across the electromagnetic spectrum, providing a diagnostic tool for studying plasmid activity. By analyzing this radiation, astronomers can infer the properties of the plasmids and the environments in which they form. This approach has been instrumental in identifying plasmid-like structures in distant astrophysical systems. One of the most exciting areas of plasmid research involves their potential connections to cosmic ray generation. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from sources such as supernovae, black holes, and even the Sun. The exact mechanisms by which these particles achieve their extreme energies remain a mystery, but plasmids may provide a key piece of the puzzle. The magnetic reconnection events that create plasmids are known to accelerate particles efficiently, suggesting that plasmids could serve as cosmic accelerators in a variety of astrophysical settings. In interstellar and intergalactic space, plasmids might also play a role in shaping the large-scale structure of the universe. Magnetic fields permeate these vast regions, influencing the motion of gas and plasma on scales ranging from individual stars to entire galaxies. Plasmids, as localized concentrations of magnetic energy, could act as catalysts for processes like star formation and galaxy evolution. Observing these magnetic bubbles in interstellar environments could reveal how they contribute to the birth and evolution of cosmic structures. The interplay between plasmids and dark matter is another speculative but captivating area of inquiry. While dark matter remains an elusive and poorly understood component of the universe, its interaction with baryonic, normal, matter could influence the behavior of plasmids. For example, the gravitational effects of dark matter might shape the magnetic fields in which plasmids form, altering their dynamics and energy release. Investigating these potential interactions could provide new clues about the nature of dark matter and its role in the cosmos. Closer to home, plasmids offer a unique perspective on the dynamics of the Sun-Earth connection. The solar wind, a continuous stream of charged particles emanating from the Sun, interacts with Earth's magnetosphere to create a dynamic system influenced by plasmids. During geomagnetic storms, for instance, plasmids in the magnetotail release bursts of energy that can disrupt satellite operations, power grids, and communication systems. Understanding these processes is vital for developing strategies to mitigate the impacts of space weather on modern technology. Plasmids are not only found in Earth's magnetosphere but are also observed in the magnetospheres of other planets, including Jupiter and Saturn. These gas giants have much stronger magnetic fields than Earth, creating environments where plasmids exhibit unique behaviors. Observations from spacecraft like NASA's Juno mission to Jupiter have revealed large plasmids in the planet's magnetotail, providing a comparative perspective on how these structures vary across different planetary systems. These findings enhance our understanding of magnetospheric dynamics and the diverse ways in which plasmids manifest throughout the solar system. In the context of heliophysics, plasmids play a crucial role in mediating the interactions between the solar wind and planetary magnetospheres. These interactions drive a variety of space weather phenomena, from auroras to radiation belt dynamics. By studying plasmids, scientists gain a deeper understanding of the Sun's influence on the solar system and the mechanisms that govern energy and particle transport in space. This knowledge is essential for protecting astronauts, satellites, and other space-based assets from the potentially harmful effects of space weather. Plasmids also raise profound questions about the scalability of plasma physics principles. The same fundamental processes that govern plasmids in the laboratory or Earth's magnetosphere also operate on vastly larger scales in astrophysical environments. This scalability suggests that plasmid research could provide a unifying framework for understanding a wide range of plasma phenomena, from microscopic laboratory experiments to the largest structures in the universe. Despite the significant progress made in plasmid research, many mysteries remain. For example, the exact conditions that trigger plasmid formation during magnetic reconnection are not fully understood. While scientists have identified key factors, such as magnetic shear and plasma density, the interplay between these factors is complex and context-dependent. Similarly, the mechanisms that govern plasmid stability and longevity continue to challenge researchers, highlighting the need for further theoretical and experimental work. The enigmatic nature of plasmids extends into their potential to unlock universal principles of plasma behavior. These structures are like fingerprints of magnetic reconnection, forming in environments as diverse as Earth's magnetosphere, the solar corona, and intergalactic space. Their commonalities across such vastly different conditions suggest underlying rules that apply to all plasma systems, regardless of scale. By studying plasmids, scientists are gradually piecing together these universal principles, offering a more comprehensive understanding of how magnetic fields and charged particles interact in the cosmos. One of the most intriguing aspects of plasmid dynamics lies in their ability to bridge the gap between theory and observation. Magnetic reconnection, the process that generates plasmids, has been studied extensively in laboratory settings, where controlled experiments allow scientists to test hypotheses and refine models. Observations of plasmids in space provide a natural laboratory, revealing how these same principles apply in real-world environments. For example, spacecraft missions like NASA's Magnetospheric Multiscale (MMS) mission have provided unprecedented measurements of reconnection and plasmid formation in Earth's magnetosphere. These observations validate and refine theoretical models, enhancing their predictive power. On a larger scale, plasmids may hold clues to some of the most profound questions in astrophysics. For instance, the role of magnetic fields in star formation is a topic of intense debate. As gas clouds collapse under gravity to form stars, magnetic fields can either hinder or accelerate the process, depending on their configuration and strength. Plasmids, as concentrated regions of magnetic energy, could influence this process in unexpected ways. By creating localized areas of heating and particle acceleration, plasmids might help trigger or regulate star formation, shaping the birthplaces of stars and planetary systems. Another tantalizing mystery involves the interaction of plasmids with high-energy cosmic phenomena. Black holes and neutron stars, for example, are surrounded by extreme magnetic fields and plasma flows, creating conditions ripe for plasmid formation. Observations of relativistic jets, narrow beams of charged particles ejected at nearly the speed of light, suggest that plasmids may play a role in their structure and energy release. By studying the radiation emitted from these jets, astronomers can infer the properties of the plasmids within, shedding light on the mechanics of these extraordinary systems. Even the large-scale magnetic structures of galaxies might be influenced by plasmids. Magnetic fields are a ubiquitous but poorly understood component of galaxies, shaping their evolution and influencing processes like star formation and cosmic ray propagation. Plasmids could act as intermediaries in these processes, transferring energy and particles across galactic scales. Understanding their role could provide new insights into the magnetic life cycles of galaxies and the interplay between magnetic fields and baryonic matter. Plasmids are also a critical piece of the puzzle in understanding space weather. The Sun, our closest star, is a turbulent and dynamic plasma system, producing solar flares, coronal mass ejections, CMEs, and other energetic events that affect Earth and the entire solar system. Plasmids form during magnetic reconnection events in the solar corona, releasing vast amounts of energy that drive these phenomena. As these plasmids travel through space, they interact with the solar wind and planetary magnetospheres, shaping the behavior of space weather systems. Predicting these interactions is essential for protecting technological infrastructure and human activities in space. One of the most visually striking manifestations of plasmids in space weather is the aurora borealis, or northern lights. These dazzling displays are the result of charged particles from plasmids in Earth's magnetotail colliding with the atmosphere, producing light as they interact with oxygen and nitrogen molecules. While the beauty of the aurora has captivated humans for millennia, its connection to plasma dynamics highlights the profound influence these magnetic bubbles have on our planet. The study of plasmids also has implications for fusion energy research. In laboratory experiments, plasmids form during magnetic reconnection events in tokamaks and other fusion devices. Understanding how to control plasmid formation and dynamics could help scientists achieve more stable and efficient fusion reactions, bringing us closer to the dream of clean, limitless energy. The parallels between plasmids in laboratory settings and those in space provide a unique opportunity for cross-disciplinary research, advancing both astrophysics and fusion science. Despite these advances, the exact mechanics of plasmid formation remain an area of active investigation. For example, the transition from smooth, laminar reconnection to turbulent, plasmid-dominated reconnection is a key topic of study. This transition involves complex interactions between magnetic fields, plasma flows, and particle acceleration, requiring sophisticated simulations and high-resolution observations to unravel. Solving this mystery could unlock new ways to predict and control plasmid behavior in both natural and artificial systems. Another area of interest is the role of plasmids in particle transport. In astrophysical settings, plasmids can trap and accelerate charged particles, influencing their movement across magnetic field lines. This behavior is crucial for understanding cosmic ray propagation, as well as the dynamics of radiation belts around planets like Earth. By studying how plasmids interact with particles, scientists can gain new insights into the fundamental processes that govern plasma behavior in the universe. Plasmids also challenge our understanding of magnetic field topology. The formation of a plasmid represents a dramatic reconfiguration of magnetic fields, creating closed loops that trap plasma and energy. This process raises questions about how magnetic fields evolve in response to external forces, such as gravitational collapse or external magnetic pressure. Understanding these dynamics could provide new perspectives on the stability and evolution of magnetic structures in a variety of astrophysical contexts. One particularly intriguing question is whether plasmids could exist in exotic plasma environments, such as those found near the event horizons of black holes or within neutron stars. These extreme settings push the boundaries of known physics, creating conditions where plasmids might behave in entirely unexpected ways. Observing and modeling plasmids in such environments could test the limits of our understanding, revealing new phenomena and guiding the development of more advanced theories. The study of plasmids is also revealing new connections between different fields of science. For example, the principles governing plasmid formation and dynamics are closely related to those in fluid dynamics, turbulence theory, and nonlinear dynamics. By bridging these disciplines, plasmid research is fostering collaborations that enrich our understanding of complex systems. This interdisciplinary approach highlights the broader significance of plasmid studies, extending their impact far beyond astrophysics. As scientists continue to investigate plasmids, they are developing new tools and techniques to probe these elusive structures. Advances in spacecraft instrumentation, such as high-resolution magnetometers and plasma analyzers, are providing unprecedented data on plasmid behavior in space. At the same time, improvements in computer simulations are allowing researchers to model plasmid dynamics with greater accuracy and detail. These efforts are paving the way for a deeper understanding of plasmids and their role in the universe. Plasmids, as we delve further, serve as one of the most captivating gateways to understanding universal energy dynamics. Their behavior transcends localized phenomena and touches upon cosmic-scale interactions, hinting at patterns and laws that might unify the micro- and macrocosmic realms of the universe. One of the key areas where plasmids extend their influence is in the study of turbulence, an area of physics that remains stubbornly elusive despite its ubiquity across natural and engineered systems. The chaotic nature of turbulence often masks coherent structures, and plasmids stand out as one of these structures, arising naturally in turbulent plasma flows. In the context of Earth's magnetosphere, plasmids provide an essential lens for studying energy transfer processes during geomagnetic storms. These storms, triggered by solar events, can have catastrophic effects on modern technology, disrupting satellite communications, GPS systems, and even power grids on Earth. The formation of plasmids in the magnetotail during magnetic reconnection events is a pivotal step in these storms. They act as energy reservoirs, storing and eventually releasing energy as they are ejected toward Earth or into the interplanetary medium. By understanding the life cycle of these plasmids, researchers aim to improve space weather forecasting, potentially saving billions of dollars in damages and protecting critical infrastructure. Moving beyond Earth, plasmids are increasingly recognized as key players in shaping planetary magnetospheres across the solar system. For instance, Jupiter's magnetosphere, the largest in the solar system, is a dynamic environment where plasmids regularly form and are ejected. These plasmids originate from the volcanic activity on Jupiter's moon Io, which releases vast amounts of plasma into the planet's magnetosphere. The interaction of this plasma with Jupiter's magnetic field generates plasmids, which then transport energy and particles throughout the system. Understanding these processes not only sheds light on Jupiter's magnetospheric dynamics but also provides a comparative framework for studying other planetary systems, including those around exoplanets. The presence of plasmids in interstellar and intergalactic mediums adds yet another layer of intrigue. In these vast and sparsely populated regions of space, plasmids might play a role in the transport of cosmic rays and other high-energy particles. The interstellar medium, filled with tenuous plasma, is shaped by the remnants of supernova explosions, stellar winds, and the magnetic fields of galaxies. Plasmids could act as conduits for energy transfer, influencing the distribution of matter and energy across these immense distances. By studying their role in these environments, scientists can gain insights into the large-scale structure and evolution of the universe. In addition to their physical significance, plasmids are becoming central to discussions about the role of magnetic reconnection in astrophysical explosions. Events such as gamma-ray bursts, the most energetic explosions in the universe, are thought to involve magnetic reconnection in their central engines. The rapid release of energy during these events could be driven by plasmid formation and ejection, similar to processes observed in the Sun's corona and planetary magnetospheres. If this connection is confirmed, plasmids could serve as a unifying concept for understanding energy release mechanisms across vastly different scales and environments. The influence of plasmids even extends into theoretical physics and cosmology. Some researchers speculate that plasmids might have played a role in the early universe, particularly during the epoch of reionization when the first stars and galaxies formed. During this period, the interplay between magnetic fields and plasma dynamics would have been crucial in shaping the structures we observe in the universe today. Plasmids, as localized concentrations of magnetic energy, might have facilitated the collapse of matter into stars and galaxies, acting as seeds for the large-scale structures that define the cosmos. The study of plasmids also intersects with the search for extraterrestrial life. Magnetic fields and plasma processes are essential for shielding planets from harmful cosmic radiation, creating stable environments where life can develop. Plasmids, by influencing magnetic field dynamics, could play a role in maintaining or disrupting these protective barriers. For example, the loss of Mars's global magnetic field is thought to have contributed to the erosion of its atmosphere, leaving the planet vulnerable to solar wind stripping. Understanding how plasmids interact with planetary atmospheres could provide clues about the habitability of exoplanets and the conditions necessary for life to thrive. On a more speculative note, plasmids have even been proposed as a mechanism for advanced propulsion systems in space exploration. The ability of plasmids to accelerate particles and generate powerful magnetic fields could potentially be harnessed for spacecraft propulsion. By creating controlled plasmid ejections, it might be possible to develop propulsion systems that are both efficient and capable of achieving high velocities, opening up new possibilities for interstellar travel. The future of plasmid research lies in the integration of observations, experiments, and simulations. Space missions such as the European Space Agency's Solar Orbiter and NASA's Parker Solar Probe are providing unprecedented data on plasmid formation and dynamics in the solar corona and heliosphere. Meanwhile, laboratory experiments using advanced plasma facilities are recreating plasmid phenomena under controlled conditions, allowing scientists to test and refine theoretical models. These efforts are complemented by high-resolution simulations, which can explore plasmoid behavior in extreme environments that are inaccessible to direct observation. Despite these advances, many questions about plasmids remain unanswered. For example, what determines the size and energy of a plasmid? Why do some plasmids remain stable while others fragment or dissipate? How do plasmids interact with surrounding plasma and magnetic fields over long timescales? Answering these questions will require a multidisciplinary approach, combining insights from plasma physics, astrophysics, and computational science. Plasmids are more than just magnetic bubbles. They are windows into the fundamental processes that shape our universe. From the smallest laboratory plasmas to the largest cosmic structures, they reveal the dynamic interplay between magnetic fields, charged particles, and energy. As research into plasmids continues, these enigmatic structures will undoubtedly provide new insights, not only into the mysteries of space but also into the underlying principles that govern the behavior of matter and energy in all their forms. The journey to fully unravel the role of plasmids takes us even deeper into the most mysterious regions of our universe. Beyond their immediate physical manifestations, plasmids challenge us to rethink fundamental aspects of plasma physics and magnetohydrodynamics. At their core, plasmids serve as a bridge between microphysical processes, such as particle acceleration and plasma instabilities, and macro-level phenomena, such as energy transfer across vast cosmic distances. This bridging role places them at the heart of many unsolved puzzles, both practical and theoretical. One of the most intriguing aspects of plasmids is their inherent ability to accelerate particles to astonishing speeds. This process, often observed during magnetic reconnection events, is not merely a curiosity but a critical mechanism for understanding cosmic particle acceleration. Charged particles caught within a plasmid's magnetic field lines can be rapidly energized as the magnetic field twists and collapses. These accelerated particles, often reaching relativistic speeds, contribute to phenomena such as cosmic rays, auroras, and even radiation belts around planets. Cosmic rays, in particular, remain a profound mystery in astrophysics. These high-energy particles, composed primarily of protons, electrons, and atomic nuclei, bombard Earth from all directions, carrying energy far beyond what can be produced in human-made accelerators. Plasmids are thought to be one of the natural accelerators responsible for cosmic rays, particularly in regions like supernova remnants and active galactic nuclei. By studying the relationship between plasmids and particle acceleration, researchers hope to unlock the secrets of cosmic rays' origins, potentially revealing new sources of energy in the universe. Another critical frontier in plasmid research lies in their role within galactic-scale magnetic fields. Galaxies, including our Milky Way, are permeated by magnetic fields that influence the motion of gas, stars, and cosmic rays. These fields are generated and maintained by a process known as the galactic dynamo, which involves the stretching, twisting, and folding of magnetic field lines within rotating and turbulent plasma. Plasmids, as dynamic magnetic structures, are thought to play a crucial role in this dynamo process, helping to transfer energy and restructure magnetic fields on galactic scales. Plasmids also provide insights into the enigmatic phenomenon of magnetic turbulence. Turbulence is ubiquitous in nature, from the swirling of smoke in the air to the chaotic flow of plasma in the sun's corona. In plasma turbulence, magnetic fields interact with charged particles in complex and unpredictable ways, giving rise to structures like plasmids. These structures, despite their chaotic origins, often exhibit surprising regularity, forming in predictable patterns and scales. By studying plasmids within turbulent plasmas, scientists aim to uncover universal principles governing turbulence, which could have applications in fields ranging from astrophysics to fusion energy research. The study of plasmids is not limited to natural phenomena. It also has practical implications for human technology. In fusion reactors, which aim to replicate the energy-producing processes of stars, magnetic reconnection and plasmid formation can lead to sudden and potentially damaging energy releases. Understanding and controlling these processes is essential for achieving stable and efficient fusion, a goal that could revolutionize energy production on Earth. Plasmid research in laboratory settings provides valuable data for designing and optimizing fusion reactors, bringing us closer to harnessing the power of the stars. In addition to their role in fusion energy, plasmids have implications for space exploration. As humanity ventures farther into the solar system and beyond, understanding plasmid dynamics becomes increasingly important for protecting spacecraft and astronauts from space weather hazards. For example, plasmids generated during magnetic reconnection events in the solar wind can create high-energy particle streams that pose radiation risks. By studying these processes, scientists can develop better shielding technologies and improve mission planning to ensure the safety of future explorers. On a more speculative note, some researchers have proposed that plasmids could be harnessed as a natural energy source. The immense energy contained within a plasmid's magnetic field could, in theory, be extracted and converted into usable power. While this idea is still in its infancy, it represents a tantalizing possibility for the future, where advanced technologies might tap into plasmids as a renewable energy resource, both on Earth and in space. As we continue to study plasmids, their connections to other cosmic phenomena become increasingly apparent. For example, plasmids are thought to play a role in the formation of jets, narrow beams of plasma that are ejected from the poles of black holes, neutron stars, and other compact objects. These jets, which can extend for thousands of light years, are among the most energetic structures in the universe. The interaction between plasmids, magnetic fields, and plasma flows in the vicinity of these objects provides a key to understanding how such immense energies are channeled and directed. Plasmids also intersect with the study of dark matter and dark energy, the mysterious components that together account for about 95% of the universe's mass-energy content. While plasmids themselves are not directly related to dark matter or dark energy, their behavior in magnetic fields and plasma flows provides a valuable model for studying the dynamics of unseen forces and structures. For example, the motion of plasmids in galaxy clusters could mimic the effects of dark matter, offering new ways to test and refine existing theories. In the realm of interstellar travel, plasmids might even hold the key to developing advanced propulsion systems. The natural acceleration of particles within plasmids suggests a potential mechanism for creating high-speed plasma flows, which could be harnessed to propel spacecraft across vast distances. By studying how plasmids form, evolve, and release energy, engineers might one day design propulsion systems that rival the efficiency and speed of theoretical concepts like warp drives and solar sails. Despite their small size compared to cosmic scales, plasmids embody the interplay of forces that govern the universe. They remind us that even the most localized and transient phenomena can have far-reaching implications, connecting the behavior of particles, fields, and energies across scales that range from microscopic to intergalactic. As we continue to explore the mysteries of plasmids, we are not just studying magnetic bubbles in space. We are uncovering the threads that weave the fabric of the cosmos itself. The vast significance of plasmids extends far beyond their immediate interactions with magnetic fields and plasma. They are intrinsic to understanding some of the universe's most fundamental mechanisms, from the formation of stars and planets to the evolution of galaxies. By delving deeper into these magnetic bubbles, we may uncover answers to questions that have puzzled humanity for centuries and set the stage for breakthroughs in technology, energy, and space exploration. One particularly fascinating aspect of plasmids is their potential role in the earliest stages of star formation. Stars are born in dense molecular clouds, where gravity pulls gas and dust together to form a protostar. The process, however, is far from straightforward. Magnetic fields in these clouds often resist the collapse of material, creating complex interactions between gravitational forces, turbulence, and magnetism. Plasmids may act as conduits for magnetic energy dissipation, allowing the cloud to collapse more efficiently. By breaking magnetic field lines and enabling reconnection, plasmids could be key players in overcoming this magnetic braking effect, facilitating the birth of new stars. Additionally, plasmids may influence the formation of planetary systems. During the early stages of a planetary disk's evolution, magnetic fields drive the movement of gas and dust. Plasmids generated by reconnection events could redistribute material within the disk, affecting the aggregation of planetesimals and, ultimately, the architecture of a planetary system. The role of plasmids in this context is still speculative, but their ability to transfer energy and matter makes them an intriguing factor in the complex dynamics of planet formation. On larger scales, plasmids contribute to the behavior of accretion disks around black holes and neutron stars. These disks, composed of infalling gas and plasma, are highly magnetized and turbulent environments. Magnetic reconnection within the disk can lead to the formation of plasmids, which then accelerate particles and emit powerful bursts of radiation. These bursts, observed as X-rays or gamma rays, provide crucial clues about the conditions near these extreme objects. By studying the behavior of plasmids in accretion disks, astronomers can gain insights into the nature of black holes, the origin of high-energy astrophysical phenomena, and the fundamental physics of spacetime. Plasmids also play a role in shaping galactic winds, the massive outflows of gas that escape from galaxies into intergalactic space. These winds, driven by processes such as supernova explosions and active galactic nuclei, help regulate star formation by removing gas from galaxies. Magnetic reconnection and plasmid formation in these winds can influence their structure and energy distribution, affecting how galaxies evolve over time. Understanding these processes is critical for constructing accurate models of galaxy formation and evolution. In the context of cosmic magnetism, plasmids are essential for studying magnetic field generation and maintenance on the largest scales. The universe is filled with magnetic fields, from the tiny fields of individual stars to the vast fields that span galaxy clusters. These fields are thought to be amplified by dynamo processes, in which plasmids play a pivotal role. By facilitating magnetic reconnection and energy transfer, plasmids help sustain the dynamo effect, ensuring that magnetic fields remain strong and active over billions of years. On an even more speculative frontier, plasmids may provide clues to the enigmatic nature of intergalactic filaments, the massive structures that form the cosmic web. These filaments, composed of gas, plasma, and dark matter, connect galaxies across vast distances. Magnetic fields within these filaments are poorly understood, but plasmids could be involved in shaping their dynamics. By studying plasmids in intergalactic contexts, researchers may uncover new insights into the formation and evolution of the cosmic web, one of the largest-scale structures in the universe. The study of plasmids is not limited to theoretical or observational astrophysics. Laboratory experiments on Earth provide valuable opportunities to investigate plasmoid behavior under controlled conditions. Facilities such as tokamaks and laser-driven plasma experiments simulate magnetic reconnection and plasmid formation, allowing scientists to observe these processes in real time. These experiments not only advance our understanding of plasmids but also contribute to the development of practical technologies, such as fusion energy and plasma-based propulsion systems. In the realm of fusion energy, plasmids are both a challenge and an opportunity. Magnetic reconnection in fusion devices can lead to sudden energy releases, which must be managed to ensure reactor stability. At the same time, understanding plasmid dynamics could enable more efficient energy transfer within the plasma, improving reactor performance. By mastering plasmid control, researchers aim to unlock the full potential of fusion as a clean and virtually limitless energy source. Plasmids also hold promise for space propulsion technologies. The natural acceleration of particles within plasmids suggests new methods for generating high-speed plasma flows. These flows could be harnessed for advanced propulsion systems, enabling faster and more efficient space travel. Such technologies would be essential for exploring distant planets, moons, and even interstellar destinations, paving the way for humanity's expansion into the cosmos. The implications of plasmids extend even further, touching on some of the most profound questions about the nature of the universe. For instance, plasmids challenge our understanding of chaos and order in natural systems. Despite their seemingly random formation, plasmids often exhibit regularity and self-organization, suggesting underlying principles that govern their behavior. Exploring these principles could reveal new insights into the laws of physics, offering a deeper understanding of how the universe operates on both small and large scales. Plasmids also inspire new approaches to studying complexity in astrophysical systems. As dynamic, multi-scale structures, they embody the interplay of forces that shape the cosmos. By analyzing plasmids, researchers can develop better models of complex phenomena, from the behavior of solar storms to the dynamics of galaxy clusters. These models have practical applications, such as improving space weather predictions and designing more resilient spacecraft. Perhaps most intriguingly, plasmids serve as a reminder of the interconnectedness of the universe. Their formation and evolution are shaped by processes that span scales from the subatomic to the cosmic, linking the behavior of individual particles to the structure of galaxies. In this sense, plasmids encapsulate the essence of astrophysics, the quest to understand how the smallest and largest elements of the universe are connected. The study of plasmids is still in its infancy, with many questions remaining unanswered. What triggers their formation? How do they evolve over time? What role do they play in the universe's most energetic and mysterious phenomena? As researchers continue to investigate these questions, they are not only deepening our understanding of plasmids, but also uncovering new layers of complexity in the cosmos. Plasmids are more than just magnetic bubbles in space. They are windows into the fundamental forces that shape the universe, offering a glimpse into the intricate dance of energy, matter, and magnetism. By studying plasmids, we are not just exploring a single phenomenon, we are embarking on a journey to understand the cosmos itself, one magnetic bubble at a time. The exploration of plasmids remains a frontier of science, revealing how these seemingly simple magnetic bubbles encapsulate immense complexity. To truly grasp their significance, we must delve further into their roles across various cosmic and terrestrial environments, as well as the cutting-edge tools and theories used to study them. Plasmids are not just passive structures. They are active agents in some of the universe's most profound and energetic events. One of the most captivating areas of research involves plasmids in the context of space weather. Space weather refers to the conditions in space that are influenced by the sun's activity, such as solar flares, coronal mass ejections, CMEs, and the solar wind. These phenomena interact with Earth's magnetic field, sometimes creating stunning auroras, but also posing threats to satellites, power grids, and communication systems. Plasmids are central to understanding and predicting these interactions. When a solar flare occurs, the sun's magnetic field undergoes a dramatic rearrangement, releasing enormous amounts of energy. Magnetic reconnection, the process at the heart of this rearrangement, produces plasmids as a byproduct. These plasmids are then ejected into space as part of the solar wind or embedded within CMEs. By tracking the formation and motion of these plasmids, scientists can gain insights into the energy dynamics of solar eruptions and refine their models of space weather forecasting. Earth's magnetosphere, the magnetic shield that protects our planet from solar wind, also relies on plasmids for its structure and behavior. During geomagnetic storms, which occur when solar activity disturbs Earth's magnetosphere, plasmids form in the magnetotail, the elongated region of the magnetosphere that stretches away from the Sun. These plasmids can travel toward Earth, triggering auroral displays and energizing particles in the radiation belts. However, they can also contribute to the loss of atmospheric particles into space, impacting long-term planetary conditions. Plasmids in the magnetosphere serve as both indicators and drivers of space weather events. Monitoring them in real time has become a priority for space agencies, as it helps mitigate risks to satellites and other infrastructure. Instruments aboard spacecraft like NASA's Themis, Time History of Events and Macro-Scale Interactions During Substorms, have been invaluable in observing plasmid formation and dynamics, providing a clearer picture of their role in geomagnetic storms. Beyond Earth's immediate environment, plasmids are also present in the magnetospheres of other planets, such as Jupiter and Saturn. These gas giants have magnetic fields far more powerful than Earth's, creating vast magnetospheres that interact with their moons, rings, and the solar wind. Plasmids in these systems contribute to the transport of charged particles, shaping the radiation belts and influencing the behavior of auroras on these planets. Studying plasmids in such diverse settings helps scientists understand the universal principles governing magnetic field interactions. Moving farther out, plasmids play a role in the heliosphere, the vast bubble of solar wind that encases our solar system. At the heliosphere's boundary, where the solar wind meets the interstellar medium, magnetic reconnection creates plasmids that mediate the transfer of energy and particles across this interface. This process is crucial for understanding the heliosphere's structure and how it shields the solar system from cosmic rays and other interstellar phenomena. The study of plasmids is not limited to our solar system. They are also observed in astrophysical jets, the narrow beams of matter and energy emitted by objects such as black holes, neutron stars, and young stars. These jets are often magnetized and highly dynamic, with plasmids forming as a result of reconnection events along the jet's axis. The plasmids accelerate particles to near light speeds, generating high-energy radiation that can be detected across vast distances. By analyzing the emission patterns of these jets, astronomers can infer the properties of the plasmids within them, shedding light on the extreme environments near compact objects. Plasmids even contribute to the evolution of galaxies. In the turbulent environments of galactic centers, magnetic reconnection generates plasmids that help dissipate magnetic energy and regulate star formation. They may also play a role in the feedback processes driven by supermassive black holes, which influence the distribution of gas and stars throughout the galaxy. Understanding these processes is essential for piecing together the life cycle of galaxies and the large-scale structure of the universe. On the theoretical side, plasmids challenge our understanding of plasma physics. Traditional models often assume that magnetic reconnection occurs uniformly across a system, but the formation of plasmids introduces a level of granularity and unpredictability. Theories of turbulence and chaos are increasingly being applied to explain plasmid behavior, highlighting their connection to broader principles of nonlinear dynamics. Numerical simulations have become a vital tool for studying plasmids, allowing researchers to explore their behavior in environments that are difficult or impossible to observe directly. Advanced computational techniques simulate plasmid formation and evolution in 3 dimensions, revealing intricate patterns of motion, energy transfer, and interaction. These simulations not only enhance our understanding of plasmids, but also provide benchmarks for interpreting observational data. Laboratory experiments have also contributed to our knowledge of plasmids. Facilities like the Magnetic Reconnection Experiment, MRX, at Princeton Plasma Physics Laboratory replicate plasmid formation under controlled conditions, enabling detailed studies of their properties. These experiments bridge the gap between theoretical models and astronomical observations, offering a holistic view of plasmid dynamics. In addition to their scientific significance, plasmids hold potential for technological innovation. Their ability to concentrate and transfer energy could inspire new designs for plasma-based propulsion systems, fusion reactors, and advanced communication technologies. For instance, understanding how plasmids accelerate particles could lead to more efficient methods of generating high-energy beams for scientific and industrial applications. As we continue to explore plasmids, the questions they raise become increasingly profound. What are the limits of their energy storage and release? How do they interact with dark matter and other unknown components of the universe? Could they play a role in processes we have yet to discover, such as the formation of exotic states of matter or the behavior of plasma in extradimensional spaces? The pursuit of answers to these questions will require a multidisciplinary approach, combining observational astronomy, laboratory physics, computational modeling, and theoretical innovation. It will also depend on the development of new technologies, such as more sensitive instruments for detecting magnetic fields and high-resolution imaging systems for observing plasmids in distant environments. As we stand on the cusp of these discoveries, one thing is clear: plasmids are not just a phenomenon to be studied but a key to unlocking deeper truths about the universe. They remind us that even in the vastness of space, seemingly small structures can have an outsized impact on the cosmos. By understanding plasmids, we are not only expanding our knowledge of astrophysics, but also taking another step toward unraveling the mysteries of existence itself. Plasmids represent a bridge between the microcosmic and macrocosmic phenomena of the universe, encapsulating how minute changes in magnetic fields and plasma dynamics can scale to influence systems as vast as galaxies or as localized as Earth's magnetosphere. The more we delve into their intricacies, the more they reveal a deep interconnectedness between physical processes spanning unimaginable distances and energies. One of the most critical aspects of plasmid research lies in their role in particle acceleration. Plasmids, acting as reservoirs of magnetic energy, can accelerate particles to relativistic speeds through mechanisms such as magnetic reconnection. These particles, often protons or electrons, interact with their surroundings in dramatic ways, generating X-rays, gamma rays, or synchrotron radiation detectable across the universe. This capability makes plasmids crucial in explaining some of the highest energy phenomena in astrophysics, including gamma-ray bursts, pulsar wind nebulae, and even the enigmatic ultra-high-energy cosmic rays. Cosmic rays, for example, are charged particles that travel through space at nearly the speed of light. They originate from a variety of sources, from supernova remnants to active galactic nuclei. Plasmids, through their rapid magnetic field rearrangements, provide a plausible mechanism for accelerating these particles to the extraordinary energies observed. Scientists studying cosmic rays often look for the telltale signs of plasmid-driven acceleration, such as characteristic energy spectra or directional patterns that point back to potential plasmid-rich environments. In the field of solar physics, plasmids are central to understanding coronal mass ejections, CMEs. These massive expulsions of solar material can carry billions of tons of plasma into space, creating geomagnetic storms when they collide with Earth's magnetosphere. Embedded within CMEs are plasmids, acting as both carriers and amplifiers of the CME's magnetic energy. By studying these plasmids, researchers aim to develop predictive models that could one day forecast the intensity and trajectory of CMEs with greater precision, potentially sparing Earth from catastrophic disruptions to power grids, satellites, and communication networks. Even within the Sun itself, plasmids play an intriguing role in maintaining the solar cycle. The Sun's magnetic field undergoes an 11-year cycle of reversal, during which the activity of sunspots, flares, and CMEs waxes and wanes. Magnetic reconnection in the Sun's corona, driven by the interactions of its internal magnetic field, leads to the formation of plasmids. These plasmids may act as conduits for transferring magnetic energy from the Sun's interior to its surface, helping sustain the cycle's periodicity. Understanding this interplay is vital for decoding the Sun's behavior and its broader implications for the solar system. Beyond our solar neighborhood, plasmids contribute to the structure of interstellar and intergalactic space. The interstellar medium, composed of gas, dust, and magnetic fields, serves as the cradle of star formation. Plasmids, generated through turbulence and magnetic reconnection within molecular clouds, can compress matter and initiate the collapse of gas into protostars. Their influence on these processes demonstrates how even seemingly small-scale features can catalyze the birth of entire star systems. Intergalactic plasmids, on an even grander scale, appear in the tenuous plasma filling the space between galaxies. Magnetic reconnection in these regions can create plasmids that influence the distribution of baryonic matter, the normal matter made up of protons, neutrons, and electrons. These plasmids may also contribute to the cosmic web, the vast network of filaments that links galaxies together. By tracing the magnetic fields and plasmid dynamics in these regions, scientists hope to uncover the role plasmids play in shaping the universe's large-scale structure. One particularly fascinating area of study is the connection between plasmids and black holes. In the accretion disks of black holes, where gas and dust spiral inward under extreme gravitational forces, magnetic reconnection generates plasmids. These plasmids are not merely passive bystanders. They actively contribute to the energetic outflows and jets often observed emanating from black holes. These jets, visible across millions of light years, owe much of their collimated power to plasmid-driven particle acceleration. Similarly, plasmids are thought to play a role in the enigmatic coronae of black holes. These coronae are regions of superheated plasma near the event horizon, emitting high-energy X-rays. The intermittent formation and destruction of plasmids within these coronae provide a mechanism for their erratic and variable emissions, offering insights into the extreme physics operating in these environments. At the forefront of plasmid research is the pursuit of understanding their dynamics in laboratory settings. While astrophysical plasmids operate on scales far beyond human constructs, laboratory plasmids provide a manageable and controlled environment to study their properties. Experiments conducted in tokamaks, devices designed for nuclear fusion research, often generate plasmids as part of the plasma's magnetic confinement process. These controlled settings have yielded invaluable data on the behavior of plasmids under varying magnetic and plasma conditions, which can then be applied to astrophysical contexts. In recent years, technological advances have transformed plasmid research. Instruments like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are capturing unprecedented data on solar plasmids, while radio telescopes such as the Square Kilometre Array (SKA) aim to detect plasmids in distant galaxies. High-performance computing has also enabled simulations that can replicate the complex dynamics of plasmoid formation and evolution, providing theoretical insights that complement observational efforts. Yet, for all the progress, plasmids remain shrouded in mystery. Questions about their role in dark matter interactions, their potential as energy storage mechanisms, and their contribution to cosmic evolution challenge existing models and demand new perspectives. Could plasmids provide clues about the missing matter in the universe? Are they part of a universal mechanism that governs energy transfer across vastly different scales? These tantalizing possibilities keep plasmids at the cutting edge of scientific inquiry. As we look to the future, plasmids may well become a linchpin in unifying disparate branches of science. From their practical implications in technology to their fundamental role in cosmic processes, plasmids invite us to reconsider the boundaries of what we know and what we can imagine. They are more than just magnetic bubbles in space. They are windows into the universe's profound and interconnected workings, reminding us that even the smallest structures can have the biggest stories to tell. As we continue to uncover the mysteries of plasmids, we are left to wonder about their potential applications in both fundamental physics and practical technology. In the realms of energy production, for example, plasmids could one day serve as a foundation for new forms of power generation. The key to harnessing the energy of plasmids lies in understanding their behavior and controlling their dynamics. With magnetic fields playing such a crucial role, it is conceivable that advances in fusion research and plasma confinement could leverage plasmids to create more efficient energy sources, reducing humanity's reliance on fossil fuels and potentially unlocking new frontiers in sustainable power. One speculative application of plasmids is in space propulsion. Space agencies around the world are working tirelessly to develop new methods of space travel that are more efficient and capable of reaching further into the cosmos. The manipulation of plasmids in space could one day be used as a form of propulsion. If researchers can develop a way to stabilize and direct plasmids within a spacecraft, they might be able to utilize the energy stored within these magnetic bubbles to propel the vehicle at previously unattainable speeds. This concept is still very much in the realm of science fiction, but as our understanding of plasmids deepens, such technology may no longer seem so far-fetched. In the broader context of space exploration, plasmids could also offer new insights into cosmic phenomena that we can only observe from a distance. For example, the study of plasmids could lead to a deeper understanding of the conditions surrounding black holes, supernovae, and neutron stars. By observing how plasmids form, interact, and dissipate in the high-energy environments around these celestial objects, scientists can glean crucial information about the physical processes at play in these extreme conditions. In the case of black holes, for instance, plasmids could help researchers understand the behavior of the plasma near the event horizon and the mechanisms behind the powerful jets that extend light years into space. Another critical area of research where plasmids could play a role is in the study of magnetospheres. A magnetosphere is the region of space around a planet or star where its magnetic field dominates the movement of charged particles. Earth's magnetosphere, for instance, protects us from the solar wind, a constant flow of charged particles emitted by the sun. Plasmids form in Earth's magnetosphere during geomagnetic storms, providing scientists with a unique opportunity to study their effects in a relatively accessible environment. Studying the plasmids within Earth's magnetosphere has implications for understanding space weather and its potential impact on modern technology. A significant geomagnetic storm could disrupt satellite communications, GPS systems, and even power grids. By studying plasmids and the mechanisms behind their formation, scientists can improve predictive models for space weather, helping to mitigate the impact of such storms on our increasingly connected world. In addition to their practical applications, plasmids also play an important role in advancing our knowledge of plasma physics. Plasma, often referred to as the fourth state of matter, is an ionized gas consisting of positively charged ions and free electrons. The study of plasmids within various plasma environments helps scientists understand the behavior of plasma under different conditions. For instance, plasmids are often created during magnetic reconnection events, where opposing magnetic fields meet and reconnect, releasing vast amounts of energy. This process is responsible for solar flares and other high-energy events in the sun's corona. By studying the dynamics of plasmids during magnetic reconnection, scientists can gain insight into the behavior of plasma in both astrophysical and laboratory settings. This knowledge is crucial for a range of fields, from understanding the basic physics of magnetic fields and plasma to developing more efficient fusion reactors on Earth. In particular, research into magnetic reconnection, driven in part by the study of plasmids, could unlock the secrets of controlling plasma in fusion reactors, an essential step toward realizing the dream of clean, sustainable energy. One of the more intriguing aspects of plasmids is their potential connection to the phenomenon of cosmic magnetic fields. These magnetic fields, which pervade space, are thought to play a crucial role in the formation and evolution of galaxies, stars, and even black holes. Plasmids, as magnetic bubbles, could provide important clues about the behavior of these cosmic fields, particularly in environments where magnetic reconnection occurs at immense scales. By studying plasmids and their interaction with these fields, scientists may uncover new insights into the large-scale structure of the universe. The role of plasmids in astrophysical environments has led to some groundbreaking theories about the origins of cosmic structures. In particular, plasmids may offer an explanation for certain phenomena observed in galaxy clusters and supermassive black hole jets. The high-energy processes that generate plasmids could help explain how energy and matter are transported across vast distances in the universe. Understanding this mechanism could provide a more unified theory of cosmic evolution, linking the behaviors of magnetic fields, plasma, and gravity. For all their mysteries, plasmids also raise profound philosophical and theoretical questions about the nature of the universe. What are plasmids telling us about the way the cosmos functions at its most fundamental level? The study of plasmids, with their complex interplay of magnetic fields and plasma, forces us to confront some of the deepest questions in physics. How does matter behave at extreme scales? How does the universe balance the forces of electromagnetism, gravity, and nuclear forces in such a way that life and structure can emerge? These questions, though far from answered, represent the core of scientific inquiry and will continue to guide research for generations to come. In the grand scheme of the universe, plasmids may seem like small-scale phenomena, magnetic bubbles that form and dissipate in the blink of an eye. Yet, their influence stretches across the cosmos, from the sun's coronal storms to the farthest reaches of intergalactic space. As we continue to explore the fundamental physics behind plasmids and their many roles in the universe, we will no doubt uncover new layers of understanding that shape our view of the cosmos and our place within it. In the coming decades, the study of plasmids will undoubtedly lead to breakthroughs in both theoretical and practical science. Their influence on space weather, particle acceleration, and cosmic energy flow will become increasingly relevant as we venture further into space exploration and as we continue to advance our technologies here on Earth. By understanding plasmids, we open the door to new possibilities in energy, propulsion, and our broader understanding of the universe. So, while plasmids may currently remain one of the more enigmatic and complex aspects of astrophysical science, they represent a frontier that, once fully understood, could transform our grasp of space, energy, and the very fabric of the universe itself. In the end, the study of plasmids may not only help us understand the distant reaches of space but also provide the key to harnessing the immense power of the universe, bridging the gap between theoretical physics and tangible technological advancements. As we dive deeper into the understanding of plasmids, the implications extend far beyond the realm of theoretical physics and energy generation. One of the most profound aspects of studying plasmids is how they could challenge and expand our understanding of space itself. These magnetic bubbles, as fleeting as they are, offer a glimpse into the powerful forces that govern not just our solar system, but the universe at large. In examining plasmids, we also begin to question the way magnetic fields work within different environments. One of the most perplexing discoveries of recent years is how magnetic fields in space are often far more complex and dynamic than we previously thought. Plasmids provide a window into the intricate behavior of these fields, especially in highly energetic environments like solar flares and the interactions between solar wind and planetary magnetospheres. We also see that plasmids are not just limited to the Sun and Earth. They are present across a wide range of celestial bodies, influencing everything from star formation to the behavior of magnetospheres around distant exoplanets. When a star forms, it creates not only light and heat but also vast magnetic fields that shape the environment around it. The plasma and magnetic field interactions give rise to plasmids, creating bubbles that can carry enormous amounts of energy and affect the way stars evolve. One particularly intriguing area of study is how plasmids contribute to the formation and dynamics of supernovae. These explosive events, which mark the death of massive stars, release immense amounts of energy, and plasmids are thought to play a significant role in this process. As the star's core collapses and its magnetic field intensifies, plasmids could form in the outer layers, driving the violent outflows of energy that characterize supernovae. Understanding how plasmids form and behave during these events could not only help us better comprehend stellar evolution but also shed light on the nature of some of the most energetic phenomena in the universe. The role of plasmids in star formation is another area of active research. As interstellar gas clouds collapse to form new stars, they often carry with them magnetic fields that can give rise to plasmids. These magnetic bubbles could help in the transfer of energy, shaping the star's birth and affecting the surrounding environment. Furthermore, plasmids might even play a role in regulating the rate of star formation itself, as they are intimately tied to the pressure and temperature conditions in the gas clouds. Through these processes, plasmids could be instrumental in shaping the life cycles of stars and the galaxies in which they reside. Another fascinating area where plasmids are being studied is within the context of black holes and their accretion disks. A black hole's accretion disk is a swirling mass of gas and dust that spirals toward the event horizon, and it is one of the most extreme environments known to humanity. Within these disks, plasmids may form as magnetic fields are twisted and amplified by the immense gravitational forces. These plasmids could influence the rate at which matter is pulled into the black hole and may even affect the direction of the relativistic jets that are ejected from the poles of some black holes. As we look toward the future, it's clear that the study of plasmids will continue to evolve. New space missions, better telescopes, and more advanced computer models are all helping scientists piece together the puzzle of how these magnetic bubbles form and interact with their environments. Instruments like the Parker Solar Probe, which is studying the Sun's outer atmosphere up close, may provide new insights into the role of plasmids in solar activity and the Sun's magnetic field. Meanwhile, efforts to explore the magnetospheres of other planets, like Jupiter and Saturn, may offer more data on how plasmids behave in the magnetic environments of giant planets. In addition to space exploration, plasma research on Earth is also advancing rapidly. One area where plasmids are being studied in terrestrial settings is in plasma confinement for fusion reactors. Scientists working on fusion energy, which seeks to replicate the energy-generating processes of the Sun, are increasingly focusing on plasmids as a potential way to control and stabilize the high-temperature plasma inside fusion reactors. If plasmids can be manipulated effectively, they could play a key role in creating more stable and efficient fusion reactions, which might eventually lead to a new era of clean, virtually limitless energy. Even more exciting are the advancements in understanding the behavior of plasmids through simulation and experimentation. High-powered laser facilities, such as the National Ignition Facility, NIF, are enabling the creation of controlled plasma conditions that mimic those found in space. These experiments give scientists a chance to study plasmids in a controlled environment, allowing for the direct observation of their behavior under different conditions. By understanding how plasmids form, interact, and dissipate in these experiments, scientists are gaining valuable insights into the forces at play in both the laboratory and the cosmos. The study of plasmids, while still in its early stages, is already revealing that these magnetic bubbles could hold the key to many questions about the universe. Their impact spans everything from solar flares to planetary magnetic fields to black hole dynamics, and they may even hold the answers to questions about the formation of the very stars and galaxies that fill the cosmos. The more we learn about plasmids, the more we understand the intricate connections between magnetic fields, plasma, and the fundamental forces that govern our universe. Plasmids are far from being mere curiosities of space. They are integral to the behavior of plasma and magnetic fields across the universe. From the formation of stars and the death throes of massive supernovae to the magnetic shields of planets and the mysteries of black holes, plasmids offer valuable insights into the way the universe works at its most fundamental level. As our tools for observing space improve and our knowledge of plasma physics advances, it's likely that plasmids will continue to play a crucial role in shaping our understanding of the cosmos. What started as a puzzling phenomenon has now become a key piece of the cosmic puzzle, one that could unlock new realms of discovery in physics, energy, and space exploration. The future of plasmid research holds tremendous promise, and as scientists continue to probe these magnetic bubbles, we are bound to uncover even more astounding revelations about the nature of the universe and the forces that shape it. The next time you gaze up at the stars, you might wonder, what invisible forces are at play, shaping the very fabric of space itself? And as we venture deeper into the mysteries of plasmids, it's clear that the more we learn, the more our understanding of the universe will expand, forever changing the way we view the cosmos and our place within it. As our exploration of plasmids deepens, the potential applications for understanding these magnetic phenomena expand, touching not only on theoretical physics but also on practical technologies that could shape the future of human space exploration. The implications of plasmids extend far beyond merely understanding cosmic phenomena. Scientists are now considering how this knowledge can be applied here on Earth. Let's delve further into the cutting-edge research on plasmids and the long-term possibilities they present. One promising area of research lies in the development of advanced space propulsion systems. Traditional propulsion methods are limited by the amount of fuel that can be carried and used over long distances. However, understanding plasmids and their energy-generating properties could potentially lead to new methods of propulsion that leverage plasma dynamics. The magnetic fields associated with plasmids could one day be harnessed to propel spacecraft at unprecedented speeds, possibly even allowing for interstellar travel. Imagine a spacecraft equipped with a system designed to generate and control plasmids. These magnetic bubbles could, in theory, be used to manipulate the surrounding plasma and create thrust without the need for traditional fuel. This concept is still far from being realized, but the idea is gaining traction in the scientific community, particularly among those working on the future of space exploration. If plasmids can be effectively controlled, they may offer a solution to the long-standing problem of propulsion efficiency in deep space travel. Moreover, plasmids' potential role in energy generation is another exciting prospect that holds far-reaching implications. On Earth, harnessing plasma energy, particularly from fusion reactions, is considered one of the most promising avenues for clean energy. Plasmids, as stable, self-contained plasma structures, could potentially be used in future fusion reactors to improve the efficiency and sustainability of energy production. By controlling plasmids in a laboratory setting, scientists could create the ideal conditions for nuclear fusion, where atomic nuclei fuse to release vast amounts of energy, similar to the process that powers the sun. A breakthrough in understanding plasmoid behavior could thus help overcome the technical barriers that have plagued fusion energy research for decades. Beyond energy generation, plasmids could have applications in advanced manufacturing and materials science. Plasma-based technologies are already used in the production of semiconductors, surface treatments, and the creation of advanced materials with unique properties. By studying plasmids, researchers could develop new techniques to manipulate and control plasma more precisely, leading to innovations in manufacturing processes. This could open doors to new types of materials and structures that are lighter, stronger, and more resistant to heat and wear. The applications of plasmid research also extend to medicine, particularly in the field of medical imaging and radiation treatment. Plasma-based devices, such as plasma arcs, are already being explored as tools for targeted radiation therapy, where the plasma could be used to treat tumors with high precision while minimizing damage to surrounding healthy tissue. Understanding plasmids in space could lead to the development of more advanced plasma-based technologies in the medical field, opening new possibilities for non-invasive treatments and imaging techniques. While all of these practical applications are exciting, it is essential to acknowledge that the study of plasmids is still in its infancy. Much of what we know about plasmids is based on theoretical models and simulations, with only limited experimental data to support these ideas. The formation, behavior, and interaction of plasmids with other plasma and magnetic field structures are complex processes that require sophisticated tools to study. However, advancements in technology, such as high-powered lasers, better computer simulations, and more sensitive sensors, are enabling scientists to probe these phenomena in ways that were once unimaginable. One of the most significant challenges in plasmid research is the difficulty in directly observing these phenomena. Plasmids are fleeting and highly dynamic, often lasting only a few milliseconds before dissipating. This transient nature makes it difficult for scientists to capture detailed data about them. However, new techniques are being developed to observe plasmids in real time. For example, Advanced imaging systems that utilize specialized cameras capable of capturing rapid events in space are beginning to provide clearer pictures of plasmid activity. Additionally, spacecraft like NASA's Parker Solar Probe, which is currently studying the Sun's corona, are helping scientists observe plasma and magnetic fields in unprecedented detail, shedding light on the conditions that lead to plasmid formation. In parallel with these advancements, theoretical models are becoming more refined. As our computational power increases, so too does our ability to simulate the behavior of plasmids in various environments. These simulations allow researchers to predict the conditions under which plasmids form and how they evolve over time, helping to guide experimental research and refine our understanding of the complex dynamics at play. Looking ahead, the study of plasmids may also intersect with our understanding of the very fabric of the universe itself. Plasma physics, and particularly the study of magnetic fields and their interactions with plasma, could one day offer answers to some of the most profound questions in cosmology. For instance, plasmids may hold clues about the formation of cosmic structures such as galaxies and clusters of galaxies. By investigating how plasmids influence the transfer of energy and matter in these structures, scientists could gain new insights into the evolution of the universe. Furthermore, plasmids could help us answer questions about the origin of cosmic rays, high-energy particles that bombard Earth from space. Understanding how magnetic fields interact with plasma in different regions of space could reveal the mechanisms behind the acceleration of these particles, helping scientists better predict space weather and protect astronauts and spacecraft from radiation exposure. There is also the possibility that plasmids could play a role in the search for extraterrestrial life. As we study exoplanets and their magnetospheres, understanding how plasmids behave in these environments could give us a deeper understanding of the conditions necessary for life to exist. Magnetic fields are crucial in protecting planets from harmful cosmic radiation, and plasmids may influence the strength and stability of these fields. By studying plasmids in the context of exoplanets, we may gain insights into the habitability of distant worlds and the potential for life beyond Earth. Plasmids are not just an intriguing phenomenon to be observed from a distance. They are powerful, dynamic structures that influence the behavior of plasma and magnetic fields across the universe. From solar flares to planetary magnetospheres to the mysteries of black holes, plasmids are present in some of the most energetic and complex environments known to humanity. As our understanding of plasmids deepens, we are likely to unlock new insights into the fundamental forces that govern the universe and uncover new ways to harness the power of plasma and magnetic fields for practical applications. While we are still in the early stages of exploring plasmids, their potential is vast, spanning fields as diverse as space propulsion, energy generation, materials science, medicine, and more. As technology continues to advance, the mysteries surrounding plasmids will likely unfold, leading to breakthroughs that could transform the way we understand the universe and interact with the forces of nature. The study of plasmids is a reminder that the universe is not just a passive space of stars and planets, but an active, dynamic system where forces and phenomena interact in ways we are only beginning to comprehend. And as we continue to explore the magnetic bubbles that float through space, we may find that plasmids are not just an interesting curiosity, but a key to unlocking some of the most profound secrets of the cosmos. As we continue to peel back the layers of understanding surrounding plasmids, it's crucial to explore the relationship between these fascinating magnetic bubbles and the fundamental forces that shape the universe. Plasmids are not just curiosities, they are manifestations of the intricate and dynamic processes that occur when plasma interacts with magnetic fields in extraordinary ways. To fully appreciate their significance, we must delve deeper into the science of plasma, magnetic fields, and their interplay. At the most basic level, plasma is often referred to as the fourth state of matter. Unlike solids, liquids, and gases, plasma is a collection of charged particles, electrons and ions, that exists in a highly energetic state. This makes plasma inherently reactive to magnetic and electric fields, and it is this interaction that gives rise to plasmids. A plasmid forms when a bundle of plasma becomes encapsulated by a magnetic field, creating a self-contained, dynamic structure that can exhibit remarkable behaviors. Understanding plasmids requires a grasp of the broader field of magnetohydrodynamics, MHD, which is the study of the magnetic properties and behavior of electrically conducting fluids, such as plasmas. MHD plays a critical role in explaining how plasmids form and evolve in different environments, whether it's within the Sun's corona, the Earth's magnetosphere, or in the vast stretches of interstellar space. When plasma is confined by a magnetic field, it can form structures ranging from simple magnetic bubbles to complex, swirling plasmids that contain vast amounts of energy and material. In solar flares, for example, plasmids play a pivotal role in the release of energy. Solar flares are violent eruptions on the Sun's surface that release enormous amounts of radiation and charged particles into space. These events are often associated with the movement of plasmids within the Sun's magnetic field. The magnetic fields in the Sun's corona can become twisted and unstable, creating conditions that allow plasmids to form. When these plasmids are ejected, they can release vast amounts of energy, impacting space weather, Earth's magnetosphere, and even our technological systems. The relationship between plasmids and solar flares also highlights the importance of understanding how these magnetic structures can influence space weather. Space weather, in turn, has a direct impact on our planet and our technology. Solar flares, coronal mass ejections, CMEs, and other phenomena associated with plasmids can disrupt satellite communications, GPS systems, and even power grids. Understanding the dynamics of plasmids and their role in solar activity is essential for predicting and mitigating the effects of space weather on Earth. Another area where plasmids play a crucial role is in planetary magnetospheres. Earth's magnetosphere, the protective bubble of magnetic fields surrounding our planet, shields us from harmful cosmic radiation and solar wind. This magnetic shield is not static but constantly interacting with the charged particles in space. Plasmids can form within this magnetosphere, particularly during geomagnetic storms, when the Earth's magnetic field undergoes sudden disturbances. These plasmids, often referred to as magnetic bubbles, can be responsible for some of the most dramatic space weather events, such as the auroras that light up the polar skies. While Earth's magnetosphere is a well-known example, plasmids are also observed in the magnetospheres of other planets. Jupiter's magnetosphere, for instance, is one of the largest and most powerful in the solar system. The interactions between Jupiter's strong magnetic field and the plasma in space lead to the formation of plasmids that play a critical role in the planet's space weather dynamics. Understanding how plasmids behave in these extreme environments can provide valuable insights into the complex interactions between planets and their magnetic fields. Beyond our solar system, plasmids also exist in the vast expanses of interstellar space. Here, they are often associated with regions of space where strong magnetic fields are present, such as in the remnants of supernovae or around active galactic nuclei. In these environments, plasmids can be far more energetic and complex than those found in the solar system. The energy contained within these interstellar plasmids is staggering, and understanding their formation and behavior can provide critical information about the evolution of galaxies, the formation of cosmic structures, and the life cycles of stars. One particularly fascinating aspect of plasmids is their potential connection to dark matter and dark energy. These elusive substances make up the majority of the universe's mass and energy, yet they remain largely invisible to our current observational tools. However, some scientists speculate that plasmids may play a role in revealing the presence of dark matter. The behavior of plasmids in regions of space where dark matter is thought to exist could offer indirect evidence of its presence. Additionally, the interaction of plasmids with dark energy, the mysterious force thought to be driving the accelerated expansion of the universe, could provide new insights into the nature of this enigmatic component of the cosmos. As our observational techniques continue to improve, and as we develop more sophisticated tools to study space, plasmids may become one of the key phenomena that help us unlock the mysteries of the universe. The future of plasmid research lies not only in understanding the details of these magnetic bubbles but also in exploring their potential applications in space exploration, energy production, and even our understanding of fundamental physics. The ability to harness plasmids, to control their energy, and to utilize their properties could change the course of human space exploration and the technologies that power our world. For example, plasmids could be used to develop new kinds of energy sources that are cleaner and more efficient than current technologies. Fusion energy, which mimics the processes that power the sun, is often seen as the holy grail of energy production. However, creating the conditions for controlled fusion on Earth has proven to be incredibly difficult. Plasmids could offer a potential solution to this challenge by providing a way to contain and stabilize the plasma in fusion reactors. If scientists can master the behavior of plasmids, we may be able to unlock a virtually limitless source of clean energy. In addition, plasmids could be harnessed for space propulsion, as previously mentioned. Traditional rocket engines rely on chemical reactions to generate thrust, which limits the speed and range of spacecraft. By studying plasmids, scientists could develop methods to use magnetic fields to accelerate plasma and propel spacecraft to much higher speeds. This could make interstellar travel a reality, allowing humanity to explore distant stars and planets in ways that were once the stuff of science fiction. As we look to the future, the study of plasmids will undoubtedly play a key role in our understanding of the universe. Their ability to store and release vast amounts of energy, their role in shaping the behavior of plasma, and their potential applications in space technology make them a central focus of cutting-edge research. While we are still in the early stages of uncovering the full scope of plasmoid phenomena, the discoveries that lie ahead promise to be revolutionary. In summary, plasmids are far more than just curious phenomena that scientists observe in space. They are the key to understanding some of the most powerful and energetic processes in the universe. From their role in solar flares and planetary magnetospheres to their potential applications in energy generation and space propulsion, plasmids are a fundamental part of the cosmic landscape. As our knowledge of plasmids continues to evolve, so too will our understanding of the forces that shape the universe and the technologies that will allow humanity to explore and harness those forces. The future of plasmid research is limitless, and the discoveries we make today will lay the groundwork for the innovations of tomorrow. In many ways, the study of plasmids is just beginning, and as we continue to unlock their secrets, we may find that the answers to some of the most profound questions about space, energy, and the nature of the universe itself lie hidden within these magnetic bubbles. As we dive deeper into the exploration of plasmids, it's essential to take a closer look at their potential to revolutionize our understanding not just of the cosmos, but also of technologies that might shape humanity's future. While the existence of plasmids is well documented, many of their intricate properties remain mysterious, which is why their study could lead to breakthroughs in areas far beyond traditional space research. One of the most compelling prospects is their potential application in space-based power generation. Plasmids, as we've seen, are magnetic bubbles that contain immense energy, often released in solar flares or during geomagnetic storms. The idea of harnessing this energy could change the way we think about power generation both in space and on Earth. In space, especially during long-duration missions, astronauts rely on solar panels for their energy needs. However, these panels are susceptible to solar radiation and disruptions caused by solar storms. If we could learn to harness the power of plasmids, essentially magnetic fields containing plasma, it could provide a new form of energy production that is less susceptible to the unpredictable nature of space weather. Plasmid energy storage, if it could be successfully developed, could provide a solution to the storage problems that plague current energy systems on Earth as well. Right now, storing energy generated by solar or wind power is a challenge because of the limitations of current battery technologies. By studying the mechanisms that drive plasmids in space, scientists may find ways to store and release energy much more efficiently, opening up new possibilities for energy production on Earth. This could make renewable energy sources much more practical and reliable, significantly reducing humanity's dependence on fossil fuels. In the realm of space exploration, plasmids offer new possibilities for propulsion systems. The idea of using magnetic fields to accelerate charged particles is not new. There have been ongoing efforts to develop ion thrusters and other forms of electric propulsion. However, plasmids could potentially take this idea to the next level. By harnessing the power of plasmids, spacecraft could be propelled using high-energy plasma contained within magnetic fields. This would eliminate the need for conventional chemical rockets, allowing for much more efficient propulsion systems that could accelerate spacecraft to speeds that are currently unattainable. Imagine the possibility of sending missions to distant stars or even other galaxies with the help of plasmids. The limiting factor in our current space exploration efforts is speed. Traditional rockets can only achieve so much velocity before they reach their limits. But with plasmid-based propulsion systems, spacecraft could travel at much higher speeds, drastically reducing travel times to distant planets and stars. This could open up the entire galaxy to exploration, making humanity's presence in space not just a dream, but a reality. While the idea of using plasmids for energy storage or space propulsion is incredibly exciting, it is important to recognize that we are still in the early stages of understanding these phenomena. A lot of the research into plasmids is theoretical, with many questions still unanswered. How exactly do plasmids form in different environments? What are the precise conditions that cause plasmids to release their energy? And can we control that process? These are just a few of the many unanswered questions that continue to drive scientists to study plasmids with increasing intensity. Yet, despite the challenges, there are already significant breakthroughs being made in plasmid research. Space missions such as NASA's Parker Solar Probe, which is exploring the Sun's corona, are providing valuable insights into the behavior of plasmas and magnetic fields. This mission, among others, is helping scientists observe the Sun's magnetic field up close, shedding light on the role of plasmids in solar flares and coronal mass ejections. These findings could ultimately help us understand not only the Sun but also how plasmids function in other areas of space, including around other stars and in intergalactic space. At the same time, on Earth, advancements in plasma physics are bringing us closer to harnessing the energy contained in plasmids. For instance, research into magnetic confinement fusion, a process inspired by the Sun's ability to contain its plasma within magnetic fields, could one day lead to the development of fusion reactors capable of producing clean, virtually limitless energy. These efforts are directly related to understanding how plasmids behave, how they can be stabilized, and how their energy can be contained and used for practical purposes. What makes plasmids so intriguing is not just their potential for energy production or propulsion, but also their ability to tell us more about the fundamental forces that govern the universe. Magnetic fields, plasma, and the interplay between these forces are some of the most basic elements of astrophysical phenomena, and plasmids are one of the clearest manifestations of these interactions. Understanding how plasmids form, behave, and release energy could provide new insights into the fundamental physics of the universe, insights that could potentially challenge existing models and lead to the development of entirely new theories. One of the most exciting prospects of plasmid research is the possibility that they could provide clues to the nature of dark matter. Dark matter is an invisible substance that makes up a significant portion of the universe's mass, yet we cannot directly observe it. Some researchers believe that plasmids may interact with dark matter in ways that are yet to be understood. If plasmids can be found in regions of space where dark matter is suspected to be concentrated, this might offer indirect evidence of its presence and provide new ways of studying this mysterious substance. Another avenue of exploration involves the relationship between plasmids and black holes. Black holes are regions of space where gravity is so intense that nothing, no matter, no light, can escape from them. However, they are also surrounded by hot plasma and magnetic fields, creating environments where plasmids could form. Studying plasmids in the vicinity of black holes could offer new insights into how these cosmic giants interact with their surroundings, and it might even help us unlock some of the secrets of how black holes themselves work. Plasmids also have the potential to reveal more about the nature of spacetime and the structure of the universe. The way that plasma behaves in the presence of strong magnetic fields could provide clues about the fundamental properties of spacetime. Scientists are already investigating the possibility that plasmids, due to their magnetic nature, could offer insights into the dynamics of space and time, potentially revealing phenomena that challenge our understanding of relativity and quantum mechanics. As we look to the future, the study of plasmids will undoubtedly continue to play a key role in the evolution of space science. Whether it's through the development of new energy technologies, the advancement of space exploration, or the exploration of fundamental physics, plasmids offer a unique window into some of the most profound mysteries of the universe. As research continues, it's likely that we will uncover even more about the role plasmids play in shaping the cosmos. The possibilities are virtually limitless. We are on the cusp of a new era of discovery, where plasmoids could help us answer some of the most pressing questions about the universe. From energy generation to space propulsion, from understanding dark matter to exploring black holes, the role of plasmids in the future of space exploration and science cannot be overstated. It's a field that promises to reveal new wonders of the cosmos and pave the way for technological advancements that could transform life on Earth and beyond. The study of plasmids may be in its early stages, but the potential for discovery is immense. As our technology and understanding of space continue to evolve, plasmids will undoubtedly remain at the forefront of scientific inquiry, offering new insights into the forces that shape our universe and helping to unlock the mysteries of space itself. The journey into the world of plasmids is just beginning, and as we venture deeper, the possibilities seem endless. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.